A physical pendulum is defined as a rigid object, meaning that the object has mass, that swings back and forth about a pivot point. Examples of a physical pendulum include the swinging arm of a grandfather clock or a swinging meter stick, as shown. A simple pendulum, on the other hand, consists of a small object or point mass that hangs from a string with negligible mass. And a torsional pendulum consists of a hanging horizontal mass suspended by a negligible string that instead of swinging back and forth, it twists back and forth around its central axis. It's important to recognize there are different types of pendulums because each has a different equation to describe its period of motion. In this video, we'll be discussing just the physical pendulum going forward. You can make a physical pendulum with a meter stick by drilling a hole somewhere in the stick and allowing it to swing back and forth from that point. The equation for the period of the physical pendulum is T equals 2 pi square root of I over mgd, where I is the rotational inertia about the pivot point, m is the mass of the object in kilograms, g is the acceleration due to gravity, and d is the distance from the pivot point to the center of mass of the object. Let's look at an example when a meter stick swings from its end. This example problem says, a meter stick swings from its end as a physical pendulum. Derive a relationship for the period of the meter stick in variables, and then calculate the period of the pendulum. So we know that the period of a physical pendulum is equal to 2 pi square root of I over mgd, but this equation is a little bit different for every physical pendulum because the distribution of mass may be different. So in our example, we have a meter stick, which can be approximated as a thin rod, and we know that the rotational inertia of a thin rod is 1/3 ml squared. So we always need to think through the rotational inertia first. Then we also need to think through the value for D. So notice I put a little cm here standing for center of mass. That reminds me that it's not just a distance, but it's the distance from the pivot point to the center of mass. In the case of a meter stick, the pivot point to the center of mass would be at the 50 centimeter mark of the meter stick, but since I have to do this in variables, I'm just going to write it generically, that the D value would be equal to 1/2 L, the length of the meter stick. So now we're going to take these, I'll call them equations, and we're going to plug them in for these respective variables. So when I do that over here, the rotational inertia has now been replaced with 1/3 ml squared, and for D, I have 1/2 of L. And obviously I kept the mg. So now I kind of have a mess going on underneath the square root sign. So I just did my algebra multiplying by the reciprocal and ended up with 2 ml squared on the top and 3 mgl on the bottom. Notice that I have an m term on top and an m term on bottom. So they're going to cancel. So I canceled an m. And I also have an L squared and an L, so we can cancel an L. And you can see that I have 2 pi square root of 2L over 3G. So this is a derived relationship for the period of this particular meter stick when it is oscillating about its end. So now I can use my derived relationship to do part B, where it says calculate the period of the pendulum. So plugging in the length of the meter stick for L is 1 meter, G 9.8, and we find out that the period of the meter stick, the time it takes to swing back and forth one time, is 1.64 seconds. Now let's look at a slightly more complicated example. Let's pretend that this time someone drilled the hole 20 centimeters from the end of the meter stick. This example says, calculate the period of a meter stick that pivots 20 centimeters from the end of the stick. So again, we know the equation for the period of a physical pendulum, but we're going to have to think through the rotational inertia value and the D value. Let's start with rotational inertia. So this time we have a meter stick. It's not pivoting through its center, which that's a 1/12 ml squared. and it's not pivoting about its end, which is a 1/3 ml squared. So that means that we're going to have to use the parallel axis theorem. So let's look at that. So we have the I value is going to be a 1/12 ml squared. That would be the meter stick pivoting through its center. Plus, we're going to have the shift on here, the rotational inertia of the shift, which is an L squared, and that L value is the distance from the center of mass to the pivot point. So since the hole was drilled 20 centimeters from the end, we now know to the middle is going to be 0.3 meters. So that's the length of my shift. So plugging in the values, I have 1/12 ml squared, and that's the length of a meter stick, 1 meter. And I have a 0.3 squared for my shift, but I don't know what m is. So I just kept that as a variable. So I have a rotational inertia value of 0.1733 m. And now thinking about distance, D is going to be the distance from the pivot point to the center of mass, which is pretty easy to see in this picture. That's going to be 0.3. So now I'm ready to plug in these values into my equation. So I'm going to plug in the 0.1733 m, and in the denominator I have mgd, so I have an m, 9.8 times 0.3, and yes, this is a capital M and this is a lowercase m, but I know that each of those m's respectively stand for the mass of the meter stick, so those m's are going to cancel. And then doing my remaining algebra, the period of this meter stick pivoting about the 80 centimeter mark is 1.53 seconds. Let's look at one more example before we move on. This time we have a physical pendulum that resembles the timing mechanism of a grandfather clock. The problem reads, a pendulum consists of a 0.85 kilogram uniform disc with a radius of 10 centimeters that is attached to a 0.2 kilogram uniform rod with a length of 0.5 meters. What is the period of this pendulum? So again, we know the equation for the period of a physical pendulum, but we have to think through the I and the D values. Let's start with the rotational inertia. This time we have a pendulum that's made of connected objects. We have a thin rod and we also have a disc. So I know that the rotational inertia of a rod pivoting about its end is a 1/3 ml squared. I also know the rotational inertia of a disc about its center is a 1/2 mr squared, but it's not pivoting about its center. It's pivoting about this end way up here, which means that there's going to be a shift involved, and we're using the parallel axis theorem. So I wrote that as ml squared. So in the next step, we can just plug in our numbers now. So we have 1/3, this is the mass of the rod, the length of the rod, plus 1/2 the mass of the disc, plus the radius of the disc. And it's the disc that is being shifted. We are shifting its axis of rotation. So the mass of the disc again is 0.85. And how far are we shifting its axis of rotation? All the way up to the pivot point, which is going to be the length of the rod plus the length of the rod plus the radius of the disc. And so doing all my number crunching, I came up with a rotational inertia value of 0.33 kilogram meter squared. So we found the rotational inertia. Next, let's find the value for D. We know that D stands for the distance from the pivot point to the center of mass. The problem is we don't know where the center of mass of this collection of objects is. So what I like to do is I like to draw an x-axis from the pivot point, call that point 0, and pretend that this is an x-axis. So we can figure out where the center of mass is by looking at each individual object. I know that the rod, the center of mass of the rod is going to be in the middle of the rod, and the center of mass of the disc is going to be in the center of the disc. And so now if we look at this as an x-axis, we can use the center of mass equation, where we have the mass of the rod, x will be this distance to here, mass of the disk is this distance to here, divided by the sum of both objects. So plugging in our numbers, we have the mass of the rod is 0.2. On the x-axis, how far is it from 0? That's going to be the center of the rod, so it's going to be a distance of 0.25 meters. Plus the mass of the disk is 0.85. And how far away is that center of mass value? That's going to be the length of the rod plus the radius of the disk, which turns out to be 0.6. And then we add the respective masses together, and I get a center of mass of 0.53 meters. Let's put that on our picture. We can see that it's slightly toward the end of the disk. So now we know the D value. And once you have those two values, it's pretty easy then to calculate the period, and we get a period of 1.55 seconds to swing back and forth one time. A simple pendulum is really a special type of physical pendulum, one that has a massless rod. Therefore, the period of a simple pendulum can be derived from the physical pendulum equation. Let's look at that. So when you have a simple pendulum, we have a point mass on a massless string. So the rotational inertia for a point mass is an mr squared. But the r is the distance to the pivot point. So in this picture, I could call that an ml squared. And then the value of d is the distance from the pivot point to the center of mass. And all of the mass of a simple pendulum is concentrated at that point mass. So the d value could be written as L. So let's now plug these values in this equation. When we do that, we have a rotational inertia of ml squared, and then we have mg, and the d value we are now calling L. And so you can see that the mass of the pendulum bob is going to cancel out, and so is one of these L's, and we end up with 2 pi squared of L over G, which is the equation that we have been using for a simple pendulum. So again, a simple pendulum is really a special type of physical pendulum. The restoring force aims to return the physical pendulum to its equilibrium position. And just like the simple pendulum, the restoring force is the y component of the weight vector mg. So the restoring force of a simple pendulum and a physical pendulum is equal to mg sine theta.